And I would be remiss if I did not mention the Doppler shift. Doppler shift is fun. It's about motion and the fact that frequency and wavelength will change if either the observer or the source of the sound is in motion. Okay, suppose we had a sound source. So we got something that's emitting pulses of sound, and it's traveling in this, I don't know why I chose left, but it's traveling that way. And so first it's here, then it's there, then it's there, then it's there. At each place it's going to emit a pulse of sound. Let's say this is a car and we're looking down on the car moving, and then the car is honking its horn or something. So honk number one will happen, and that pulse of sound after some time will move out in all directions at the speed of sound from that place of emission. So I tried to draw this circle with the center right at dot number one. So then the car moves on to dot number two, and it's going to emit a pulse. There won't be as much time because we've had a time step between 1 and 2 to let the car move. So it'll be a smaller circle, hopefully centered around dot number 2. And then dot number 3, an even smaller circle around dot 3, and then dot 4, an even smaller circle there. So if you look at the wavelengths on the leading edge, they're crowded together as opposed to the wavelengths here. Within the limits of my drawing abilities are stretched out. And so we have longer wavelengths over here, shorter wavelengths over here. But of course we have a formula that relates wavelength and frequency. So if the speed of sound in air is constant, which it roughly is, then if we have a shorter wavelength, that means we have a higher frequency. So if you happen to be ahead of the car and listening from that perspective, then you're going to hear these shorter waves, which come in at shorter wavelengths and higher frequency. So in the human hearing system, a higher frequency is a higher pitch. So you'll experience a higher pitch from a car coming toward you. But if the observer happens to be the other direction over here and the car is receding away from you, you've got longer wavelengths and a lower pitch. And so that's a familiar experience you've probably had in your life, that a passing car will, as it approaches, will have a higher pitch, and then as it goes away, it has a lower pitch. Of course, there is a formula for this. So the frequency change, so the one you hear, we'll call that observed. And then the one that you would hear if everything was stationary, or if you were just located on the source itself, that's the reference frequency. That's not what you observe necessarily, but that's the true pitch that's happening, and that's equal to the velocity of sound in air divided by the velocity of sound in air plus or minus the velocity of the source away from or toward the observer. And that's what this plus or minus is for. This is by convention negative for toward the observer. So if the source is moving toward the observer, that is a negative. An astronomer would call that a blue shift. And it's positive for motion away from the observer. And it's totally okay to forget which is which until you're used to it, but that is the convention. That's how things are going. Now suppose if the problem statement didn't have frequencies in it, what do? Well, you go up and notice this awesome equation here, which relates frequency to wavelength. And the medium determines the speed of sound. So your speed of sound, v sub w, no matter what medium you're in, you should be able to look up what the speed of sound is. So Doppler effect super useful for anything from astronomy to radar guns to check for speeders, and then interesting experiments in physics class where you get to hear the pitch change as an object moves.